Today we're going to be looking at VLANs, Virtual Local Area Networks. A VLAN is a partition, a layer 2 segment of the OSI model. Multiple VLANs can coexist. Each VLAN is a broadcast domain, typically with its own IP subnet. Here's the most important thing. A virtual local area network is an isolated segment of your network. You must have a layer 3 device to move user data between VLANs. VLANs survive inside switches. That's what switches do, create and separate VLANs. All the users that live on a VLAN have no idea they're part of a virtual local area network. No idea at all. Think a bit of a history lesson. Cast your mind back. Let's say we had a 3-story building and the CEO's up on the 3rd floor and he's got his own special network and he can have all the special rights he needs. And there's a flood and he needs fresh carpet. So they move him down to the 2nd floor. He's on a whole different network now. Different rights, different privileges. Doesn't have what he needs. But in the new VLAN model, the network is virtualized and it can move to wherever it needs to be. The switches control the virtualization, the VLANs, and one router will be routing between each of those VLANs. You're no longer geographically limited to the physical space. Benefits of VLANs. Here we have 6 PCs, PC 1, 2 and 3, 4, 5 and 6. When PC 1 wants to talk to PC 4, the traffic goes into the switch. It's encapsulated into a trunk, we'll talk about that in a minute. Goes up to switch 1, down to switch 3, and then out on port 11 to PC 4. When PC 2 wants to speak to PC 5, it goes into switch 2, up to switch 1, down to switch 3, and out to PC 5. PC 3, PC 6, exactly the same way. Now here's the most important thing. When PC 1 wants to talk to PC 2, that traffic goes into the switch, it goes up to switch 1. It goes into the router. It gets routed from one VLAN onto the next VLAN and back down onto VLAN 20, then onto switch 1, back down to switch 2, and then out to PC 2. If we took that router out of the picture and just turned it off, PC 1 and 4 can talk, PC 2 and 5 can talk, PC 3 and 6 can talk. But it is absolutely impossible for PC 1 to talk to PC 2 or PC 3 without that layer 3 device, without that router present. That's the power of the switching, keeping those VLANs isolated from each other. You must have a router to route between VLANs. So, a bit of a jump ahead in our skills, but we'll go there anyway. The show VLAN command, one of my favorite commands. Let's look at the output of a show VLAN command. It shows the VLAN number, the VLAN name, its status, and what ports is associated with. So let's do a bit of Q&A. So, how many VLANs are there in total? Pause the video and answer the question. There are 10 VLANs. How many of VLANs have we created? How many VLANs has the administrator created? We've only created 5. VLAN 100, 150, 160, 200, and 555. Is there anything wrong with a marketing VLAN? No, there's just no ports actively configured. Remember, VLANs exist across your network, so it just happens on this one switch. There's no marketing VLAN ports. Now, can PCs on port 3 and PCs on port 16 communicate with each other right now, just on this one switch all by itself? Yes, because if you look, both ports 3 and 16 exist on the sales VLAN. So they're on the same layer 2 segment, so they can absolutely talk to each other. Now, for a trick question, which ports are actively trunking? So pause the video for a few seconds and see if you can figure it out. Sorry, it's a trick question. Ports 23 and 24 are currently actively trunking because the show VLAN command shows you what ports exist on what VLANs. But a trunk does not exist on one VLAN. It exists on multiple VLANs. Therefore, ports 23 and 24 are not displayed in this output. Trunking. The 802.1q protocol is by far the most common method of trunking at the moment. So if you look on the switches on the right, you've got 4 switches. Between the bottom switch and the second switch, there are 3 different VLANs: red circles, green squares, and yellow triangles. However, between the middle 2 switches, all of those shapes are all jumbled up, mingled together. And yet when they get to the other switch, they're all successfully and safely broken back out into their appropriate VLANs. This is done by placing a tag, an extra piece of information onto every single frame so that we can keep all those VLANs separate. Now there is a slightly older style of trunking called ISL or Inter-Switch Link, but even though that's Cisco proprietary, even Cisco themselves are slowly phasing it out of their equipment. So 802.1q is definitely the tagging protocol that is most heavily used. So we take our original frame. We need those 2 MAC addresses. The destination source MAC address we absolutely need. We need the type length field. We need the user data. But now the frame check sequence, we chuck that away because we need to completely recalculate it. We insert the tag in the middle of the frame. This tag contains a priority section, the token ring section, and the VLAN ID itself. These 4 bytes have been inserted into our frame. So, got 2 questions for you. Now that we've added 4 bytes to a standard Ethernet frame, what is the maximum size of an 802.1q frame? And how many possible VLANs can we have? So to answer the first question, a standard Ethernet frame maximum size is 1518 bytes. So now I've added 4 bytes. So 1522 is the standard maximum size for an 802.1q tagged frame. Now VLAN, 12 bits. 2 to the power of 12 is 4096. So we don't use 0, we start with VLAN 1. So we've got from 1 all the way up to 4095 possible VLAN identifiers. And we don't really cover it heavily today, but the priority bit at the very front is all about prioritizing traffic, voice, video, data, keeping it separate. So even at layer 2, a layer 2 switch understands to prioritize voice traffic over just normal user data. Voice VLANs, very, very important, because a while ago we had to program switch 3 as a trunk and say, okay, switch 3, you're a trunk, your encapsulation is 802.1q, your user traffic is this, your data traffic is that. And it was very, very convoluted. But now what's happening is the switch and the phone talk to each other. So you just program the switch and say, right, normal traffic is going to be on VLAN 20 and the voice traffic is going to be on VLAN 150. So the phone wakes up. It uses CDP, talks to the switch and says, hey, I'm a phone. And the switch says, hey, phone, I'm a switch. I've got important information to you. All of your voice traffic, you need to put that on VLAN 150 from now on, please. So when the PC number 5 sends his traffic, it goes through the phone and just ends up at the switch with no tagging information. And the switch says, right, that's user traffic, that's VLAN 20. But when the phone needs to make a phone call, it sends that out with the tag saying, this is voice traffic because I'm tagging it with VLAN 150. The switch will trust and accept that tag because it trusts the phone. But if you just plug a normal PC in there and try and send tag traffic to the switch will completely chuck that traffic away. The only reason why tag traffic survives is because the switch and the phone talk to each other and negotiate using CDP. It's not a trunk link. Even though tag frames are allowed, only tag frames are allowed on VLAN 150. And that's it. And only when they're coming from a phone, and the switch and the phone negotiate that. And VLAN 150, the switch knows it's the voice VLAN, so as on the previous slide, it gives it a voice priority. So as the traffic moves from switch 3 to switch 2, the priority tag is set to say it's voice traffic. So it gets priority over other traffic. Now, unfortunately, not all traffic can be tagged. So CDP, for example, spanning tree, lots of other different protocols are untaggable because they're not classic Ethernet frames. So we have this word native. That's the native VLAN. So we've got the switch in the middle, and we've got all these VLANs whizzing around, and all of those VLANs are tagged. Except we have to reserve one VLAN to say, if we're unable to tag this frame, then we'll just assume that's part of VLAN 1. Now, security. VLAN 1 is the default VLAN. And if you put PCs on that VLAN, then it's possible to inject double tagged frames and then end up on that VLAN. So there are two schools of thought. The first one is, don't use VLAN 1 for anything. That's fine. Nothing on VLAN 1, everyone's safe. The second school of thought is manually set the native VLAN to another number and make sure you never have any PCs or users on that VLAN. We'll discuss that in a little bit as well. So, how do we configure VLANs and VLAN trunking protocol? VLAN trunking protocol is a very interesting protocol because it is the information about VLANs. So Cisco have discovered, but there's a few vulnerabilities with VTP we'll talk about in a minute, but this is the way switches share with each other information about VLANs. So let's say you got 500 switches in your network and your boss comes to you and says, I need a new VLAN, create a new VLAN please. You go to the server switch and you create that VLAN. Now that switch uses VTP to share information about that change throughout all the switches in your network. But there's a problem with that, and we'll talk about that as well. So VTP mode, server. You got server, client, or transparent. VTP domain, always give it a unique domain name and always give it a unique password. And VTP pruning is just automatic pruning. We'll talk about that in a little while as well. And there are different VTP versions. That being said, what I just showed you was the old way of doing things, because the VLAN database is the classic version. So you might be out there on the Googles looking at VTP and they might say VLAN database, put in some commands and you're good to go. However, this is being deprecated. Cisco don't want you to use it anymore. Now they want you to have everything in the new school where you just go configure terminal and you start putting in the VLAN information. The reason why this is important is because the classic way, typing VLAN database, none of these commands exist in the running config. They only exist in that VLAN.dat file. So you do a show run and you can't see them. Nothing you've typed stays there. Whereas with the new school, everything's in the running config, everything's in the startup config. It's very easy to see, very easy to understand. The other thing with classic mode is you can go VLAN database and make 50 changes, and none of those changes will take until you click exit or apply. However, new school, every time you make a change, you press enter, that change is alive. That change is going. So now we're going to set up our users to use our VLANs. So switch port mode access, always good for security reasons, forcing your ports to be what you want it to be. And now we have switch port access VLAN 20. That is literally saying this port is now hard coded, that anyone plugged into this port is on VLAN 20, and that's that. Spanning tree port fast, we cover that in another session, but it's just a good best practice to do because it makes your network spring to life a bit faster. Now, the reason why it's a good idea to force switch port mode access is because if you leave that command out, someone can plug in a PC and it will automatically detect as access. But someone on that PC can run a special piece of software that will send messages to say, hey, I would like to be a trunk, please. And the switch is happy because it's not set, it's dynamic, and say, okay, sure, you can now be a trunk. And then that person who's now got a trunk link on their PC can tag manually their traffic with any VLAN ID they want, and they can get anywhere in the network they want to get. But if you say switch port mode access, that's it. Locked access mode, VLAN 20, you can't do anything about it. Now, when you have links between switches, it's best practice to force the speed to maximum and force the duplex to full. very rarely, sometimes you put two switches together and they auto-negotiate, and the auto-negotiation fails, and one end's full duplex and one end's half duplex, and it's no good. So this way, it's always best to force the speed. And just teaching you a little shortcut. So if you type switchport host, it'll actually does about 4 things, but for the sake of today, it actually adds to the running config switchport mode access and Spanish read port fast. It's like a little shortcut, little shortcut to make your life a bit easier, a bit less typing. So let's have a look at some verification commands. So we've got this interface, we've forced it into trunk mode, and we've moved the native VLAN away from the default native VLAN out to VLAN 99. So now we do show interfaces, the number of the interface. Now this is awesome. Up until today, you've probably typed show interface 100 times. But now, and when you do that, you get lots of zeros and lots of counters, bytes in and out, errors, all that sort of stuff. But now we're going to use the switchport command. The easiest way to remember this is the switchport command is a layer 2 command. So when you use it, it does layer 2 work. When you put in a show command, it shows you layer 2 information. Because when you show interfaces switchport, we don't get any counters, bytes, or traffic in and out. We just get the operational status. So it's in trunk, it's running trunk mode, its encapsulation is .1q, and the negotiation of trunking is on. We'll look at that in a minute. The trunking native VLAN is VLAN 99, and all VLANs are allowed to traverse across this trunk link. Now, I said we'd look at DTP, Dynamic Trunking Protocol, in a minute, because this is where switches can negotiate. Do they want to be a trunk or do they want to be access? The reason this is really critical is because I've got 2 switches on the screen. I've got a 3550 and a 2960. Now 2960s are manufactured to be access layer switches, so they want their ports to be accesses. 3550 series or 3500 series routers, switches, are designed to be distribution layer switches. So they're designed to talk to other switches. So when they see another switch, they want to be a trunk. So when you plug a 3550 and a 2960 into each other, we're not quite sure what's going to happen. The 2960 wants to be access, the 3550 wants to be trunk. How are they going to negotiate automatically? So, always best practice, in my opinion, to force. So switchport mode access or switchport mode trunk. However, if you like things to be automatic, you can do that. You can say switchport mode dynamic auto, switchport mode dynamic desirable. So switchport mode dynamic auto means I'll only become a trunk if someone asks me to. Whereas switchport mode dynamic desirable means I want to be a trunk and I'm going to ask everyone else to be a trunk. So I guess the analogy there is that 2960s are always dynamic auto, 3550s are always dynamic desirable. So technically, if you plug those two in together, it should come up as a trunk. But you plug two 2960s together, they're both auto, they will never ask to be a trunk, so they'll stay in access mode. And what happens when you force one end to be trunk and you force one end to be access? Well, different people say different things. In my experience, it's a lottery. It may be a trunk, it may be access, we don't know. Very dangerous. I wouldn't recommend it. And if DTP, and some people say security is paramount, so you can just turn it off. You say switchport mode access, switchport no negotiate, or switchport mode trunk, switchport no negotiate. You can just disable DTP altogether, and the port will just do exactly what you programmed it to do. So, problems with trunks, things that will stop a trunk from coming up. Native VLAN mismatches. In the good old days, it would just fail. But nowadays, thankfully, both ends will just spam the console endlessly with error messages saying, I'm native VLAN is 1, that guy's native VLAN is 100. So it's an obvious message, it's really good. Trunk mode mismatches. One could be negotiation of trunk, one could be ISL, one could be 802.1q. This will cause problems. Now, allowed VLANs is a tricky one because by default all VLANs are allowed, But if you go to one end and say only allow VLANs 10, 20, and 30, and then the other end, he'll send you traffic on VLAN 1. He'll send you traffic on VLAN 99. But your end, you'll just chuck it away because you've hard-coded that you're only allowed a handful of VLANs to work. So that's why it's also, again, just to make that show interface switch port, shows you which VLANs are allowed on that trunking interface. VLAN double tagging is a real threat. So the attacker's on VLAN 10. They tag the frame for 10 and add a second tag for VLAN 20. So when that hits the switch says, oh yeah, you're on VLAN 10, that's fine. But inside the machinations of the switch, as it goes to move it out the trunk onto the right-hand switch, it realizes that VLAN 10 is a native VLAN, and it knows it has to remove that tag of VLAN 10 because the native VLAN is untagged. So once it's removed the VLAN 10 tag, the VLAN 20 tag still remains. So it whizzes across to the right-hand side switch. The right-hand switch just sees a tagged frame with VLAN 20. So then that traffic leaves that switch on VLAN 20. So double tagging is a real threat, and the easiest way to get around it is to not have any hosts on the native VLAN. Move the native VLAN to somewhere where nobody is and never have any hosts on that native VLAN. Alright, some basic guidelines, some rules to help us get our VLANs up and running. Don't use port 1. Move everything off port 1. Or move the native VLAN to something else. Shut down all unused ports, very useful. So some rando just starts plugging stuff in, it's not going to work because those ports are disabled. Always have a separate VLAN for management, for managing your devices. Do not have the user traffic commingling with your management traffic. So you create a management VLAN, and that's the VLAN you use to manage, and make sure it's not the same as the native VLAN as well. You set up an access policy. We're going to cover access control lists in a little while. That policy restricts who in fact is allowed to manage those devices. Set up your switch to only accept SSH because Telnet is clear text and easy to be sniffed out. Disable auto negotiation on trunk ports. Like I love to say, switch port mode trunk. Do not use auto and desirable switch port modes. Force the mode to be trunk mode. Now, VLANs and routers. Why do we have these VLANs? To separate out users. But we've got to route the traffic between VLANs. So here we've got a very simple network. Nothing wrong with this network at all. We've got PC1 on VLAN 10, goes into switch 2, goes up to the router, gets routed inside router 1, onto VLAN 30, comes out on VLAN 30, everyone's good to go. Perfect, everything's fine. Because you've got the VLANs and you must have a layer 3 device to route those VLANs. This design works, but it has a very big limitation. What happens when your boss comes to you and says, yo, we need VLAN 50? Okay, so you add VLAN 50, add a third port to the router, plug it into the switch, good to go, everything's fine. And then he comes to you the next day and says, oh, we need VLAN 60, 70, and 80. Now you're getting into trouble. Because switches have got lots of interfaces, but multiple interface routers are very, very, very expensive. So we need to come up with a better way of doing this exact same thing. So the next level of this idea is a router on a stick, or a one-arm router. So now we have two VLANs on the switch and a trunk link between the switch and the router. So the traffic starts here on VLAN 10, moves up, is in the trunk with a tag, gets routed inside the router, is re-tagged with VLAN 20 in the trunk, and comes out on VLAN 20. So the router to switch link is a trunk, so only one interface is needed for multiple VLANs. The switch, however, must support VLANs and trunking. The router must support VLANs and trunking, but it's actually called, on the routers, it's called sub-interfaces. And it must be 100 megabits or faster. And it needs to support the trunking protocol, 802.1q or ISL. But as I said earlier, ISL's very underused these days. Here's the biggest downside. All the VLANs are on a single interface. So if that is a 100 meg interface and you've got two VLANs, technically speaking, each VLAN's only got 50 meg. If you've got that 100 meg trunk link and you've got 10 VLANs, then each VLAN has to share 10 meg. So the bandwidth of that trunk link now becomes critical. This is the configuration. This is actually how to program the router on a stick. So on the left hand side we have our router configuration. So we go to the major interface and we don't give it any information, no IP address, but we enable it. We enable it with no shutdown. Then we create a sub interface. It's just as simple as interface fast Ethernet 0/0.10. So that dot or full stop or period, that's the denotation that a sub interface is being created. The very next step is we enable 802.1q and we say what VLAN is associated with that sub interface. So we got VLAN 10, 172.17.10, VLAN 10, and then we got interface sub interface 30, which is on VLAN 30. So the sub interface is just created by the dot. Now let's move over to the switch. On the switching side, we've got port 5. We've set it to trunk mode and we've set the encapsulation type to .1q. We've got full speed. And then on port 6, you've said you're on port VLAN 30, and port 11, you're on VLAN 10. This works. This is everything set to go. Now, I will say one thing. The purple writing is about the native. By default, VLAN 1 is native. So, we can either have the purple for VLAN 10 on both ends, or not have it at all. So just leave the native VLAN on VLAN 1, and then everyone works, because we've got VLAN 20. So the purple writing, the word native, and the switchboard trunk native VLAN command, they either both need to be there, or neither of them needs to be there, and everything will still work. Now, here's the kicker that I've seen in lots of places. Notice that subinterface 10 is on VLAN 10, which has the IP address of 172.17.10. This does not have to be that way. You could quite easily make subinterface 99 be on VLAN 47 and be 192.168.84. But that will just drive you crazy. It doesn't have to be a standard, but I strongly recommend that you make the subinterface number the same number as the VLAN number, and whatever the VLAN number is, have some portion of that VLAN number in the IP address. It makes troubleshooting 1,000 times easier. So now we take layer 3 routing to the next step. Now we do it inside a layer 3 switch. Switches do all of their decisions in hardware, so they're very fast compared to routing. So, traffic between PC A and B, that's standard switching, staying on VLAN 10. Traffic between PC A and C, however, is routed through the routing engine of the switch, but switches do all the decisions in hardware, so it's as good as being switched at layer 3. So we set this up. First thing we need to do is turn on the layer 3 routing functionality. Typically it's disabled. So with the command IP routing, and then we go interface VLAN 10, IP address, interface VLAN 20, IP address. Now this switch is routing at layer 3 between VLANs 10 and VLANs 20 at super fast switching speeds. These interfaces, SVI, switch virtual interfaces, they're the VLAN interfaces. They're no longer just for management, they're actually forwarding user data between VLANs. SVIs, layer 3 interfaces, can set up for any VLAN. It should be the default gateway for your users, because that's what a router would be, so switches should be the same. You cannot have more than one SVI per VLAN. VLAN equals SVI. You cannot have more than one VLAN for SVI. You cannot have an SVI in control of more than one VLAN. However, you don't have to create a VLAN for every, you don't have to create a switch virtual interface for every VLAN. So there could, in this switch, be VLAN 30. And that would have to be routed by some other layer 3 device. There's nothing wrong with that at all. Alright, thank you for watching, and hope to see you in the next one.